So, dear colleagues, let's start our second day of the second week of the school. And today we will start with the topic on geological disposal of radioactive waste and the Russian experience in this field. So, Dr. Elena Savelyeva from Institute of Safety of Atomic Energy Development. Yeah, is it correct?
Nuclear safety. So, hello everybody. I'll try to speak about the final stage of nuclear fuel, the disposal, when it is already prepared for disposal, and starting with that nuclear energy is clean energy. It doesn't have emission of greenhouse gases, but still people are afraid of it. Perhaps because of lack of knowledge and understanding, or maybe they are afraid of not exact understanding what to do with the radioactive waste. So when the problem of radioactive waste appeared, there were several different proposals how to deal with it, and some of them are presented in this slide. For example, disposal in sea, disposal in the ice shield. Now they are prohibited because they are very sensitive to climate change. Already there is a proposal to launch in the space. Perhaps it is possible, but it requires some technical feasibility and perhaps the united of all activities of the human world, which seems not possible in the current situation. So at the moment, the disposal in the geological disposal is the international consensus with the storage, not long-term storage, but storage during the period while disposal facility is prepared and its safety is justified. First, it was a very optimistic solution because it was considered that two qualified geologists and one engineer can design such facility. And it is a very easy solution, but while it was involved, it appeared that a large number of different organizations, scientific organizations, construction organizations, and others need to be involved, mostly not to construct and design the disposal, but to justify that it is safe. For example, in this slide, you can see the names of basic organizations which are involved in the Russian project of the radioactive waste disposal. So to start, let's have some terminology. Disposal, it's the placement where radioactive waste is placed without intention to excavate it back. And it needs to limit some effects of waste on human and environment. The intention not to extract is always fixed, but it is not sure, you couldn't be sure that this will be fulfilled because during the construction, during the operational phase and monitoring phase, it can appear that some accidents will lead to the need of extraction of the radioactive waste. For example, such situation is in Germany with their salt disposal, where now they are working on how the disposed radioactive waste to extract them back. What is the safety? Safety is regulated by those impact on population and environment. And it doesn't need not to exceed the limits during the whole period of potential danger, very long period. So basing on the safety and disposal, we can have a sketch of geological disposal. So this is some system of engineering barriers, radioactive waste, host rock, and deep and situated rather deep, more than 300 meters, usually 500. And this need to perform safety functions such as containment, so that the radioactive waste is fixed in matrix engineering barrier and host rock as long as possible, and isolation from the biosphere, population, and environment. These are global safety functions of the disposal, which need to be fulfilled to provide the safety of the disposal. To justify that the designed facility meets the safety requirements, there is a special procedure which is called safety case. It is rather big, you can call it document or set of documents. Mostly it is set of arguments which are in the honor of the safety of your designed radioactive waste disposal facility. The main part, not total part, but the main part requires numerical modeling. It is because of diversity of influence and processes, the multiscalarity of processes and environment, both in space and time. And also you couldn't perform in situ and laboratory studies to cover all the possible situations which can appear in the facility during the long-term period of the potential danger. So all this numerical modeling is combined together and called the safety assessment. Here is the scheme, basic scheme of safety assessment. It starts with gathering, integrating, and analysis of data which are obtained for a moment. And it is an iterative process which can continue both because obtaining new data or because some safety assessments are not confirmed and or not justified, so that the regulator is satisfied. So then data are gathered, and feature importance and processes, which are mentioned as FABs, usually analyses are performed. This analysis allows to justify that all factors which are important for safety are taken into account. And basing on FABs which are selected as important for current design and current position, location of the disposal facility, it is used for constructing basic and alternative scenarios, basing on events and processes, description of initial state, which is based on features, and also checking that the available software covers all requirements to describe important processes and environment for performing the modeling. Quantitative safety assessment is model development, which is parameterization of model, validation, verification of model, uncertainty quantification. And the final result is to check if the results satisfy the norms of the country to satisfy safety functions, regard uncertainty range. So I already told that safety case is an iterative process, and it starts at the very beginning of the road to operation and closing of disposal facility. In the first stage is site selection. Usually it is started with some blank map where are indicated factors which are not favorable for disposal facilities, such as geologic negative factors, surface negative features. They mostly influence on the surface disposals and near surface disposals, but can have some effect on deep geological disposal also. And as we need to minimize the non-sanctioned human interaction, it is involved in isolation safety function of the disposal facility. We need to see that this position is not significant water supply sources and mineral deposit. After that, taking in account sociological factor and economic aspects, some potential sites are selected, and there are performed basic host rock analysis from the surface with not deep boreholes to check if the host rock satisfies basic conditions. It need to be low permeability, possibly high absorption, etc. So in Russian Federation, we already have a selected site. It is situated near Krasnoyarsk region. Here is the site and the map of the underground research facility. And you also can see the basic information on underground research facility. So the host rock is crystalline, archean gneiss. The depth is around 500 meters. The planned length of galleries is about 5 kilometers. The access is through the shafts. And the site was approved in 2016. Construction of surface facilities, surface buildings, and infrastructure started in 2018, and mining started in 2023. All activities concerning construction of the geological disposal in Russia is performed according to special document which was approved by concerned Rosatom, and it is called the strategy. It's some analog of roadmap. It covers all different aspects which are important during the preparation for operation of disposal facility. First three phases are before construction of the repository itself. They are for preparation, construction of underground research facility, and for research activities in underground research facility. At the moment, we are at the phase 2. We started to construct shafts of the underground research facility. During the phase 1, one of the most important works was to develop and detail the R&D program. It started with available data. Mostly it was based on the recommendation and expert comments obtained during the licensing of the construction of underground research facility. I didn't told that the regulator approved the site as potentially possible for underground research facility, and national operator has the license for constructing the underground research facility. Also, we took into account some guides from international organizations, Russian legislation concerning nuclear energy, international FAB catalog, and considered, as we know that models, numerical models, play a very important part in safety case, we considered that modelers need to be taken involved in program development, so that all required by models and possible to estimate at least somehow input parameters for models need to be incorporated in the program. So after that, the program was structured as a matrix, where you can see that in the rows there are parts of elements of the disposal facility, such as biosphere, geosphere, engineering barriers, radioactive waste. And at the columns, there are types of investigations: in situ studies, laboratory experiments, modeling, required equipment. In the cells, there are directions which need to be studied by these methods for this element. They are also detailed in more detailed investigations. They are distributed according to life cycle, to the time and location. And finally, some special investigations programs for different directions were developed, and now we are working according to these special programs. Also, the design and studies of the experiments which need to be performed in the underground research facility itself are under development still. And you can see here some steps. I'll talk about them later. So now I'll go to the special programs which are under development now. The first one, maybe the most important at the moment, is the scientific support of shaft and tunnel mining. So again, about the underground facility. So it is the combination of surface buildings, for example, for laboratory experiments and tests of the samples, shafts. There are 3 shafts, tunnels, which surround the basic zone, which is supposed to be the geological disposal itself. And at the tunnels, there are some chambers for long-term experiments. Also, there are mentioned some boreholes for monitoring and short investigations. So the support is dedicated to obtain the valuable information which is available only before walls are grouted. So we need to get as much information on the massive as we can, and also we couldn't slow down the mining itself very strongly. So to do this, we divided our investigations in 3 blocks. First block, it is regular investigation, which is incorporated in the cycle of mining, and it doesn't strongly slow the works. Block 2 is supposed to perform special additional experiments and studies at positions where there are some discontinuities of the rock. It will stop the mining for some time, so it needs to be planned very carefully. And block 3, it doesn't require, it can be performed after walls are already grouted. It is doesn't relate to construction cycle. Only positions where to perform these additional experiments and monitoring need to be established during mining phase. So as we have interaction interval block 2 interval investigations most influencing our mining works, we need to prepare carefully to perform them. So we have already some prepositions where to make it. And while coming closer, we need to perform the time schedule of investigations, detailed scheduling, prepare all equipment, and describe and consider in details all applied methodologies, so to make all investigations in time and don't stop more than it is required. The regular investigations mostly are devoted to geological documentations, different types of geological documentation. It's mapping, photos, 3D scanning, or considering features if they are found. And then all information is placed in the information model. I'll talk about it a little bit later also. Scanning this so that this shaft will be totally reproduced in the informational model. Also, during regular investigation, performed some sampling of rocks, of rock, of fracture fillings, of water, if there is any. Now again to interval investigations. So during the preliminary phase, the deep boreholes were drilled at the positions of shaft with core sampling, and basing on core description and other geological studies was performed the geological model. The cross-section of the part of geological model which is dedicated to the shafts is presented in the slide. The rectangles show the positions where some discontinuities of rock are expected and where the interval investigations are supposed to be performed. So coming closer to this position, which is known, we check the right position of interval investigation. Then this is the snapshot of the information model of the underground research facility. And this is the part of the shaft. And here is the current position for interval investigations. And this is the description of what is supposed to be found there and what is supposed to be done there. After we come to the position and we change it in the information model immediately. So interval investigations are mostly devoted to check the quality of the massive rock. And so the quality is usually described by permeability and stress features of the rock. So they are planned to be drilled small boreholes, horizontal and inclined boreholes. There are planned slot and stress estimation, some pumping tests, and describing of more detailed description and studies in the boreholes of the fractures if they are found. In the bottom of the slide, you can see our current vision of the total amount of interval investigations. This slide shows the equipment of studying the disturbances with acoustic mini-seismic method. This method is based on the principle of defectology. So the acoustic waves are launched, they are reflected by the boundary of the defects, and after receiving by the sensitive receiver, the position of the boundary of the disturbance can be found. This method was successfully used in the Monterey laboratory in Switzerland. For stress stain estimations, we plan to use state discharge method. It uses two measurements by stain meter before drilling the slot and after drilling the slot. And the magnitude of the stress is estimated by the formula basing on the preliminary knowledge and on the obtained estimates. So the second part and the second program deals with additional geological investigations at the site, at the far zone, and also it covers the monitoring. So first about monitoring. These features show the deployment of monitoring networks at the site position. It is here, site position, and around it. Also, to get monitoring data, we are connected to the monitoring performed by organizations which do it in the surrounding zones, and to the state monitorings of seismic and meteorological stations. This plan indicates only those posts and boreholes which were performed during our project. The monitoring covers meteorological monitoring, hydrogeological, geodynamics, and seismical. More detailed lines of geodynamical monitoring are presented in these slides. They are for detecting vertical and horizontal movements of the surface. During summer periods, starting with 2022, at the site and around started the in situ investigations in the boreholes, in old boreholes, and also drilling new boreholes. The first analyses were dedicated to hydrogeological tests, but they were preceded by acoustic lodging. The acoustic lodging was performed by Russian equipment Paros. This equipment allows to indicate fractures and features, and also possibly water permeability zones. Other anomalies also are detected, but there is a special software developed which allows to select those which are due to potential zones of hydraulic conductivity. Such positions are indicated in the slide, and their depth is also indicated here. The hydrogeological tests performed in this well confirmed that these zones are really more conductive, and this allows us to be sure that this methodology can be applied for other wells. Hydraulic injections and pumping tests were performed by a special design of packers. We checked different organizations of packers. This presented the equipment, and this figure shows that the new performed in 2022 estimation of water conductivity is lower than that was performed while basing on the preliminary analysis in the deep part. This part was not checked, so it is not the new estimate, it is only the line itself. Also, during these summer seasons, were drilled new wells with sampling, with taking the rented cores. You can see here example of cores and the panoramic due the acoustic televiewer. This video televiewer was also used in the old boreholes to check and to obtain the statistics on features. It is set down in the borehole. After that, that gives snapshots of the wall. And each snapshot is supplied with information on direction, depth, and also temperature. And it allows to use special software which make the panoramic view, then get out the lineaments and get the statistics on the fractures which can be later used for DFN modeling, for example. The combined use of acoustic optic televiewers and incrementary also allows to obtain some zones of fractures, which also can give us some information on the fracture statistics. This equipment is planned to be used for interval investigations during the mining, also together with mini-seismic approach. Samples were under the laboratory test. They were checked for mechanical, chemical, temporal properties. Here is, and also mineralogical composition. Mineralogical composition was obtained through using tomography and electronic microscope together with special database on minerals, which is a well-known approach. Here are the distribution of samples according their type and the quality of the rock. Also, water samples were checked on their chemical composition, and microbiological composition was studied for both water samples and rock samples. So the third part concerns the engineering barrier system. Investigation of engineering barrier systems in our project is divided in two parts. One is devoted to studying of containers. There is a special program for containers. And the other is the program for studying materials and composition for buffer zone and backfilling. I'm mostly talking about the buffer system because it started 2 years ago, and the program with containers is starting only now. So this investigation program can be divided in 3 parts, which are intersecting. It's selection and justification of material, investigation of impacts of the material with other materials which can be present in the engineering barrier system, and with gases and radiation from radioactive waste, and investigation of technological feasibility and organization of industrial production. They can be interconnected through the modeling, because by modeling we can consider for our concept for elements and their safety functions, the requirements to the barrier materials. Also here we can see if our requirements can be fulfilled by technological production. And if everything is good, we can discover how to organize the industrial production of the material and the constructions. So the first part, we select the safety function for a buffer. For the buffer, there are functions for protecting the container and for limitation of radioactive waste transport after the container is already damaged. The protection of container also can be divided in two parts. The mechanical protection, when we check that the buffer has the ability to of dumping the accidents which can of the accidents of the rock, and also that the it is rather stable to stabilize containers in the correct position and stop their overturning. The other protection deals with protecting it from the corrosion, mostly microbial corrosion, and this deals with special hydraulic and geochemical conditions. So also ability for self-healing after hydraulic and mechanical damage of the buffer is also important because it prevents getting water closer to the container. So these safety functions require some special features of the material which can be estimated and found and checked what what functions are fulfilled and how. So the isolating features are described by some swelling pressure, high absorption, ability to throw gases not without damage for the facility. The thermal features need to provide the ability of effective heat removal. So mechanical properties are plasticity for damping the stress of the rock, and also they need to be solid for prevent overturning. Also, chemical conditions can be favorable if they limit the microbial activity, or also if the corrosion rate of the metal container is maybe not minimal if possible, but predictable, and there will be no pitting corrosion. So the program for investigation of materials is of three parts. First part, it's basic features of the material and also of the constructions, because speaking about buffer, we also think about compacted blocks. So basic features are studied on the laboratory examples, and also on layout tests because of the scale problems. The other part deals with evolutionary features, This is how the basic features will evolve during the time, while impacts of the conditions of the radioactive waste disposal. These can be contacts with different materials, with radioactive waste, with microbes, also with water, with rock, and so on. And the last part is the migration features for radionuclides, both in basic features, but still mostly in the contact with different materials, because while radioactive waste will be out of the container, some evolution on buffer material will be already taken. So here is some slide with laboratory equipment used for studies in vessels and in small scale, also some some layout tests, larger ones. This one is for self-healing of bentonite. You can see that it was the initial state, and after filling with water, it became something like this. And this layout test is for erosion, where the boundary part of the bentonite was covered with water, and it was moved, and also it was checked on the generation of and types of generated colloids. So even if we find out and justify that there is possible material and possible production of the constructions, we need to be sure that there is enough of such material for our needs, for the total disposal facility. And that's why we started to study the disposals of available disposals of bentonite clay. There are geological criteria on the deposits based on the required features of the material. The geological criteria are on the genesis, on the depths, on the amount of material. The most preferable for a moment is the set of deposits in the Acacia. It looks as there is the bentonite of satisfied quality, and there is amount of it, available amount of it, which can cover all our needs. At least we expect so. And also the organization working or operating these deposits has the ability for production of compact bentonite blocks of different shape and size. And we are also already started studying the geotechnological features to get the production which satisfies the quality required for the buffer zone blocks. So now the last part, it is not special program, but it is a rather important part which makes possible the work of a large number of organizations. So it is information support. And I'll talk a little bit about numerical codes which we use for modeling. So for informational support, we develop the pulse system, which the project of Underground Laboratory Scientific Escort. This system is devoted to integrate all data which is obtained during the project. This data is of very different types, of different use, produced by different organizations. So we didn't try to make something universal, and we decided that the metadata-based approach is the best for us. So we download data sets of all obtained results supplied by special description, so that it can be found out who downloaded it, what is it about, who performed measurements, what was used for. So all information which can be supposed to be important for those who will use this data. The uploaded data can be downloaded by specialists for performing analysis, because usually all specialists using the same data work with the same formats, so they can understand them, and they have their software for dealing with them. Also, additional to storing the data, this system makes the links with other important informational systems which can be used by specialists. For example, it is the geological information system, which is used by geologists, hydrogeologists. It is already mentioned 3D information model, where data on construction and surrounding of the shafts is stored. It is the set of already developed numerical models with their parameters. It is so-called bank of models. But the core of the system is the so-called knowledge base, and it is composed of our R&D program, FAP lists, some requirements system which deals with international guides and Russian legislation documents. Also, there is a library, it is not indicated here, containing all reports and publications which deal with the current project. And our ambition is the digital safety case. We started this development. We consider this digital safety case as very important part of our work, because it provides the transparency, the links to all types of information directly, which are already stored in this database. All documents are stored here. So it can be very useful for both investigations, researchers, and regulators. So some examples of how it is. Here is the research matrix, how it looks in the system. All investigations, all directions of investigations have the color. By default, it is red. But when in the research item is downloaded something, for example, some report or some data, it became yellow automatically. It doesn't become green automatically. Green, it becomes only according to the expert meaning, after experts consider that some time, some part or some research is already finished. So it is fulfilled totally. Then experts make it green. This is the passport of the investigation, where it is described the contract over which it is performed, where The reports where a description concerning this investigation can be found, and some short comments describing what is it, how it was made, to what program it devoted, and also this is the indication that this current investigation is already fulfilled. The knowledge system has link to the informational model. These are figures directly from the informational system, informational model. They show the detailed equipment and including the supplies such as electricity, water supply for the current experiment, how it looks like. You can zoom it closer and closer. And this part, it is in the pulse system. There is also the figure of the underground research facility. And also you can check some chamber, and you'll get the information on the experiment which is planned in this chamber. It's the passport of the research, the same, the basic items are the same as the usual research, but also there is the possibility to see the figures obtained from the informational model. This link also allows to make modeling of the experiments, which is very important during the design of the experiments. The detailed information and models are in the pulse system. The detailed scheme of the detectors, of the heaters. Here is the example of the heater test. Are in the information system. They allow to construct the grid geometry, which can be transferred to the model. After modeling by the model which is stored in pulse system, the results of temporal cuts can be downloaded in the information model back for visualization together with the equipment and with detectors and with the geology if it is required. This model was developed, and for it were performed the sensitivity analysis, which showed that the most important for the experiment to obtain the characteristics of the rock which are required for modeling is to establish the heater at the temperature which is correspond the radioactive waste. It is the most important parameter for the model. Also, it was obtained that ventilation in the tunnel doesn't affect the results of temporal field for those detectors which are not in the tunnel. So about our first steps in the digital safety case, we consider it as some basic document with set of hyperlinks. At the moment, we doesn't have the basic document where to place the hyperlinks. So we deal only with links themselves, and we make some item where are links to the results. This is the item concerning the development of water flow in the discrete fractures, and so it requires the information on fractures and statistics of fractures, on the distribution of dikes, and so on. So this information is linked, and it is presented in some reports. Also, this model is linked with some FAPs concerning the hydrogeology, and after it is fulfilled, this FAP will be also obtaining some coloring or that it was taken into account in the model. So now a little bit about modeling. For our purposes in functionality, we are developing in our institute special numerical codes. FENIA code is for 3D thermomechanical modeling. It allows to model heat transfer, stress of rock and constructions, and estimation of strengths and packages. And stress can be estimated even taking into account the thermo-induced stresses. It was used for the project of deep geological disposal to consider the thermal stress according to the different types of distribution in the disposal containers with radioactive waste. The other code, Caride, it has two parts. One is devoted to transport of neutrons and photons, and this nuclear kinetic allows to estimate the processes in the radioactive waste according to their cooling time and irradiation performed, and estimate the temperature of radioactive waste, which can be transferred to FENIA code as the initial state of the radioactive waste. The other part is devoted to estimation of doses for environment and for staff working in the deposit. This part allows to use different scenarios of water supply and food supply, food chains, and so on. GERA code is for groundwater flow and transport modeling. It allows to construct 3D models and also profile models. It can allows to take into account different geological elements, non-isothermic features, sorption, gas generation, colloids. And now we are working on incorporation of discrete fracture networks into this as a part of this model. Chemical modeling we perform with well-known code FreeQC. We doesn't develop special our code for chemical modeling, but we developed lots of models describing the small-scale experiments, describing evolution of metal, evolution of concrete, of bentonite, and their impacts, also gas generation, and all these models take into account, if possible, macrobiological impacts. Some of these models are verified on experimental data already obtained in some laboratories, others on the literature, laboratory experiments described in literature or other literature data. And all these models are enveloped by mouse code for justification of uncertainties. This code allows to calibrate calibrate model according to available measurements, and perform uncertainty and sensitivity analysis of models. It is model-independent code because it considers model as a black box and cooperates with it by some specially organized files. But it appears that it is not directly model-independent because there are some problems which arise according to different formats of inputs and outputs of the models, and this requires considering all types of, it is not possible to consider all types of possible formats, so mouse code is somehow model independent for our set of models, our set of software, which I presented at the previous slide. But still, it can be used for other models with some special requirements. So this slide shows how we used Gera code basing on data available for at the current moment, based on geophysical analysis, small short boreholes, and other information which is structured as geological model, and then constructed the conceptual hydrogeological model. Also, it took into account some fault zones which are possible according to the geophysical estimates. You can see them from side and from the top. And here is the result of transport modeling of some not sorbing nuclide. We performed sensitivity analysis for this model by using mouse code. Here you can see the variance-based sensitivity indexes, and they indicate that the model, the ground flow model, is mostly sensitive for conductivity parameters of the fracture zones, and and infiltration rate. And the contamination transport is associated with 3 closer to the deposit possible faults. You can see here the zooming of the model where with the current position of the faults. And I know I see everybody, not everybody, but most of auditory is sleeping, so I'm finishing. And this is the last slide. I want to take your attention to our journal, which we issue in our institute. It's Radioactive Waste Journal. It's a platform for discussion on all aspects of radioactive waste management. There are lots of papers also concerning underground research facility, and still it is the platform which gives us transparency, at least among the scientific society. Also, some population, everybody can access to it, but and it is sometimes read by non-specialists too. We have the translation of this journal into English, so everybody who is interested can contact the website and see the journals. There is some gap between Russian and English versions, but it is not very large. So that's all. Thank you for your attention.
So, any questions?
Thank you for your presentation. I have a question in the slide, I think it's 40, because there you show us the evolution of the temperature underground through some models that you run. And I understand that, yeah, this one, yes. And we can see that while the time is passing, the temperature rise more. Let's say in 103 years, temperature is more than it is in 54.
Yes, but if you continue, it will fall down. I have no time. Perhaps it's better to change this one by something later, or present here the 1D graph.
So in the first, let's say 100 years, the temperature rising of the high level waste.
Yes, it is in the within the buffer zone.
Okay.
It is not the far field. It's the zone of the site.
And another thing about the vertical sections that you have made, did you have any data of where is the underground water levels?
Oh, this one.
Yeah, is here somewhere appear the water level, the underground water level?
Yes, where are some fractured zones, there is some water.
And where it is here?
I can try to see. Oh, it is in Russian. Okay. For example, here.
So, what depth is that? It's about 100 meters. What?
It's about 300 meters.
300. Thank you.
Any more questions? And I have a question regarding the Gera software. In this software, can you change the scale of the blocks that are modeled? I mean that when you have an object, you made a net, yeah. So there are
Yes.
and so you can change the size of
yes,
this.
the size of cells can be changed according to their position, and it can be more small in the closed zone, and they are larger in far zone because there is few information there at least.
Okay, thank you. If there is no other question, then let's thank the speaker again. So let's continue our school with the next lecture that will be given by Dr. Evgeny Moisenko about the uncertainty management for the long-term disposal. So,
Good
please.
morning. Good morning, ladies and gentlemen. Valentina Sutelman was supposed to give this lecture, but she could not do it. So she asked me to give this lecture, gave me the materials. So I hope I'll manage. We work quite closely with her, so let's hope that everything will go right. During the previous lecture, you got some impression about the concepts of the radioactive waste disposal, the ways of modeling of the processes that actually go or can go there under some circumstances. And I will speak more about the not modeling itself, but the approaching to the modeling with uncertainties, things we do not know or cannot fully model. Now, the most, as you have already heard, the most, the best way to dispose of the rad waste is considered to be the deep geological disposal. It seems to be a really good idea with the least chances of the effect on the environment, on the future generations. Anyway, it seems to be much better than just storing it, hoping that the future generations will do something. The concepts of the geological disposal are quite well developed already, but and it is considered to be quite safe, but there is always a catch. We're speaking about many thousands years, up to the million years, according to IAEA recommendations. And we need to assess the safety of the disposal facility for the times much longer than the lifespan of the humanity. And we have to, and we do not know what can happen in these times. But still, we have to assess it, to think about it. So as I have already said, there is need for very long-term assessment. And we need to model a large number of different processes in lots of different structures. First, naturally, they go engineered barriers, then the natural barriers, and then the environment itself, where the nuclides will eventually emerge, hopefully after very, very, very long time. When the idea is that when these nuclides reach the biosphere, their impact is much less than the impact of the natural factors. So once again, the uncertainties are inevitable, and the better we deal with them, the more reliable will be our safety assessment. Naturally, we cannot prove the safety of our disposal facility just from the experiment. There are no such long-term experiments. If we speak, for example, about concrete, the oldest concrete structure on Earth is about, well, less than 2,000 years old. It's located in Rome, at the Pantheon. we can try to assess some natural analogs like water flows through different ground, different rocks and so on, but it still has lots of uncertainties. And so our only hope is the numerical modeling. And as any model, it is simplification, which is uncertainty itself. And so why do we need, summarizing what I've said, why do we need to deal with uncertainties? First, we just do know some things about our world, and we have to assume them, and we need to make modeling, adding extra uncertainties, and the reliable management of the uncertainties yields the reliable safety assessment, the reliable safety case for the disposal facility. We model lots of different processes and they interact. There can be different classifications. For example, one, I have already mentioned it, when that's the time flow related with the nuclide flow. First, they are located in the glass matrix if we talking about the vitrified waste, or within the fuel rods if the fuel itself is disposed. Then it goes through the engineered barriers to the geosphere, and finally the biosphere. And actually, that is what should be assessed, the impact on the biosphere, on the prospective humanity. And in each of these barriers, of these areas, I would even say, the processes are interconnected. This is a very simplified scheme. It even does not include all kinds of processes, just to give the general picture. So if we speak about the engineered barriers, there is hydrogeology, which is actually influenced by thermal processes. It produces mechanical processes, rod waste characteristics. First of all, the heat generation influences thermal processes. So everything is interconnected, and then I will show you how we can deal with these complicated interconnections. So, as I have said, there are lots of possible uncertainties. And if we want to deal with them, we should first identify their sources. Since if we do not know what we try to assess, how we can assess it? Generally, we try to, if we speak about the uncertainties that are inherent to the nature, we can identify the following sources. First, is characteristics of different subsystems, like waste itself, engineered barriers, host rock, there is some sedimentary layer, processes in the biosphere. The first group is very, very simple. That is our input data, which we cannot measure perfectly. There is always inaccuracy in measurements. And the natural variability. For example, if we take the large enough block of the rock, especially crystalline rock, the properties will vary, maybe slightly, but they will. So that natural variability, which cannot be perfectly assessed, adds to the uncertainty. The more complicated source of the uncertainties is the identification of the processes. When we do the modeling, we omit some processes, either because we think them not very influencing, or because we cannot include them into our modeling, for we do not have models for these processes. There are always simplifications, interpolations and extrapolations. The simplest case, if we, for example, study corrosion, we can do experiments. We can do them, for example, for years, for dozens of years, but we have to extrapolate this process for the hundreds of years. We interpolate and extrapolate the properties of the rock, since we can study just a small number of samples, and we have to extrapolate them to the whole rock. And the interactions that I showed in the previous slides, we can sometimes we cannot fully assess these interactions. And the external events. These are the natural phenomena. Of course, we try to find the location for our disposal facilities so that these were minimized. No strong earthquakes, no predicted ice sheet, but still something can happen. And the human intrusion, that's a very complicated subject. For who knows what the civilization will be within thousands of years. But these scenarios also should be considered. And for each group of these uncertainties, so we have identified the sources very roughly now. There's a number of questions. First of all, can we assess these uncertainties numerically? For this group, it's easy. That's our measurement errors. We can more or less make estimates for them and use these estimates as our input data. And for these sources of the uncertainty, it's very hard or maybe even impossible to estimate. So in this case, well, there are some methods in the codes validation and so on. And here we can just speak in the terms of the probabilities and of the imagination. For if we want to assess some very infrequent natural phenomenon, we should imagine it. Like, I don't know, meteorite strike, incredible earthquake, some, I don't know, monster invasion, whatever. The next question is, to what extent they are significant? Maybe we can just leave them out from our consideration. This question is answered by the sensitivity analysis, and in many cases, especially in for these sources, by the expert judgment. We just sit in a group, think, make a hypothesis, and say, okay, this factor can be neglected. Well, the world works like this. And another question is, could they be avoided or reduced? For example, can we make better measurements to reduce the uncertainty of the input data? Or maybe can we reduce the effect of some of these special events, or maybe to avoid them. For like human intrusion, there is a very special area of interest in the red waste disposal. How to propagate the knowledge about this disposal facility and about its danger through many, many generations. Even if the civilization, for example, declines for some times, maybe even down to the Stone Age, and goes back to the high civilization level, when any possible information source will be lost. Speaking of the simplest, well, no. So actually, we incorporate all these uncertainties into the numerical models. But of course, we cannot incorporate all uncertainties into the one single model. So we need to split them in parts, and the highest level of our classification is the scenario. It is a sequence of events, the evolution path of the disposal facility with a given initial state and with possible influences. Then, for each scenario, there are different processes which require their own models. So the next level of the classification is models. Actually, the term model is quite complicated. There are many different models. There is a hierarchical set. So first, there goes conceptual model related with the conceptual uncertainty. There's assumptions that we make about our system. Like what should be included into the model, what can be not included, what how we treat these processes and so on. Then the next level is the mathematical model, the equations. There is another uncertainty here. Since the different equations, different correlations provide slightly or not slightly different results. So the choice of the equation results in the uncertainty. Then the next level is the numerical model, the discretization, the linearization of our equations. Once again, we introduce some error or uncertainty. Then we make the code. We can do mistakes when we write it. Potentially, there is one more source of the uncertainties just from the code. And when we run the code and obtain the numerical results, we can make errors in our input file, or there can happen something like a glitch of the computer. And once again, there is another source of uncertainty. So there are many, many of them. But speaking of the simple classification first, there is uncertainty in the choice of the scenario. Of course, we cannot consider all the possible scenarios, so we have to take the most significant ones. Then the conceptual uncertainty, what we assume about each scenario. And the simplest is the parametric uncertainty, what we use as the input data. Speaking of the scenarios, their description can be quite complicated. They can involve different systems, like and different processes, mechanics, chemistry, hydrology, thermal processes, decay, and so on and so on. Actually, there can be the third dimension, different subsystems. So it may be at least three-dimensional or even more. But about any scenario, we can say this. First, what kind of a scenario it is? The normal evolution, is that what's going to happen with our facility by design? If everything works as intended. Alternative scenarios, if there is something wrong, like some damaged containers, some unnoticed crack in the host rock, well, something predictable, the appearance of the ice sheet upon our facility. Another group is, I've already mentioned, this human intrusion scenarios. What can be done? Future generations can drill into this facility, drop some bomb, or just dig with a spade, spending hundreds of years because maybe some tale will appear that there is some unknown treasure buried underground. Nobody knows what can happen, but we need to use our imagination and develop such scenarios. And there is a special set of the scenarios, so-called what if, virtually impossible scenarios, which are still assessed, like alien intrusion, or something like that, just to test how far is the protection of, how good is the protection of our facility. So what is the most severe event that can happen with a facility without risk of the nuclide release into the environment? So this, and each of these scenarios is described by the various processes. There will be variations due to the effects. For example, if we have damaged canisters, damaged containers, there might be, for example, changes in the thermal state for the thermal release will be extended, and there will be changes in the transport, and so on and so on. So there is lots of different interconnected processes. How can we divide them, assess them? There is an approach named features, events, and processes. So we classify all the factors that can potentially influence our repository into groups. First is features. This is the simplest group. This uncertainties that's measurement accuracy, initial variability. That's mostly the properties of the different subsystems. Thermal conductivity, absorption coefficients, and so on, so on, so on. A bit more complicated thing is events. What can happen? So earthquakes, climate change, sorry, and so on. With this, we can mostly deal in statistical methods, speaking about the probability of these effects and the resulting probability of this or other outcome of our simulation and the evolution of the repository. And the processes That's a description of how we can simplify what's going on in the nature in our models. We can list which processes should be assessed and which can be neglected. And each of these groups is applied to different subsystems like waste package, repository, geosphere, biosphere, and so on. So, for example, for geosphere, there are properties, and actually, if we open some FEPS document, for example, by IAEA, there will be a list of the properties which are significant or may be significant. Then processes that may be significant and some processes. These are not requirements. So it's just an attempt of the International Society to classify, to add system to that chaos of factors. So as I have said, the processes are very strongly interconnected, and how we can deal with these interconnections. One way is to make a matrix. So we list possible processes and fill the squares on how much they influence each other. For example, we can see that the field source, the source of the nuclides affects the geosphere, and then the biosphere, and so on. So we make a matrix, and then we can split each cell once again, making our assessment more and more granular. So first, we work with large blocks, large subsystems, large groups of processes. Then, in each block, we assess in the same way different interactions, and we can go as deep as we need to understand what's going on. So the goal of this process is to understand the interconnections well enough to make models. Another approach is related not to the interconnection of the processes, but to the possible combination of the effects, for example, and of the subsystems. For example, we can assume that there are problems with the containers. So, but the geological processes are assessed correctly, and there are faults in hydrological model. Or we can assume that everything is okay, but with the containers, but a huge earthquake happened. So we combine these factors, let's place the dots, and compose a scenario. Like 10% of the containers are damaged, and there was an earthquake, and everything else is okay. Now, to the conceptual uncertainties. If we want to assess those conceptual uncertainties related with the model choice and model assumptions, we need to assess different models. We cannot, if we just pick one model without thinking about the others, we cannot assess these uncertainties. So if we take different models, do the simulations with them, then we can, even if we choose one, we can see how much the results with different models differ and understand the influence of this uncertainty on our simulation result. The choice of models can include the choice of the model processes, different approach to the description of the processes, different equations, different assumptions about the boundary conditions, like presence or absence of the glacial sheet, about the thermal heat flow from the Earth core, and so on. And another interesting aspect is the number of model parameters. The more complicated our model is, the more we should know about the object we model, the more input parameters it uses. And it adds up to the total uncertainty. Generally, when we just start the process of the repository development, we use the simplest models. They have quite few input parameters, and it allows us making general assumptions about the final state of the repository. Then, when we get more and more knowledge about the repository site, about the concept of the disposal, how we will arrange that waste, and so on, more and more elaborate models can be used. And here, uncertainty and sensitivity can be of help. For example, we learn more about our site, we use more complicated model, then add more parameters into the model, then we run the sensitivity analysis, and we find out that these new parameters do not influence the result. So we can easily switch back to more simple model. There are two main problems. First, we cannot assess all possible alternatives. So we just should live with it, but do our best to make these estimates, the biggest set of those alternatives. And another problem is that the models we choose can depend just on our facilities. One thing is when we have an access to the supercomputer and we can use very complicated models, or we have just a laptop and we can run on these simple models on it. Now we move to the level of the single model. Uncertainty management on this level is the simplest one. It's what is called the forward uncertainty propagation. First, we identify the uncertain parameters. Generally, we make the list of all input parameters of the model. And when we set the number, we think, how well do we know this number? Is it measured precisely, or there is some uncertainty in the measurement? Is the source reliable? For example, if we take the data from some graph from the book, which is 50 years old, we just can introduce the error by guessing which number this point represents. Then we quantify these uncertainties. We define the ranges of their variation. And now we can run our model multiple times with different sets of input parameters and process our results analytically. Since we have a population of the results, we can do the statistical analysis, finding its mean, its standard deviation, and so on and so on. We can run the sensitivity study to find out which input parameters are more influential and which are less influential. And as a result of this, we can reduce the uncertainty. For example, by finding out that one parameter influences most, but its uncertainty can be minimized by making better measurements, or removing from the consideration the parameters which don't influence much. You just give them a fixed value and run the code with that value. What we can do about the assessment, I have already said we can find mean and standard deviation. We can define percentiles, confidence bands. For example, if we are simulating the dose risk of the final state of our facility, we can have several curves depending on the input data at the time, well, with time. So the dose, the expected dose, it has some band. It should be noted, I have already said that we cannot assess these uncertainties by running the model only once. We need a set of data that can be statistically processed. It is named Monte Carlo approach, but that says nothing. Any approach which uses multiple random initial data is Monte Carlo. The difference is how we process these input uncertainties and what we do with our outputs. So now to the sensitivity analysis. Why should we do it? First, it's screening, not influencing parameters. So we just draw the line in the list of the parameters and say those below the line are insignificant, and we just can treat them as constants. No problem if we do not know them exactly. Then ranking. We want to know which input parameters influence most to concentrate on their study, to measure them better, for example. The related thing is the variance cutting, so that we could decrease this uncertainty range of our output. The related thing is the factor mapping, since to find out which combinations of the input parameters produce undesirable results. For example, if we have very high nuclide concentration in the matrix, and well, the simplest case, and the permeable engineered barriers. So, but where is the border? How much nuclides can we store within the matrix? And what's the limit of the barrier's permeability? In the sensitivity analysis, we can assess not just the level of the influence of the factors, but also the direction of this influence. Does it increase or decrease our value of interest? So we can identify the trends in our simulation. If we change something in the repository design, what will be the effect of on the final result without running the code? We can, by knowing how this parameter influences the result, we can find the trend, not, of course, the exact value. Well, first we'll start about how not to analyze the sensitivity. That's how it started, and sometimes this approach is still used. We take one point and do the perturbations of each variable. Practically, we find the local derivatives and consider these derivatives to be the sensitivity coefficients. Quite straightforward, but first of all, this works only if our response is linear. If it is nonlinear, especially if it is even non-monotonous, this approach will give nothing. And another problem is that when we do this, we assess the very impossible scenarios for if we make this probability density. So the most results allocated quite generally allocated quite densely around our initial value. And if we speak about these points on the borders, in some approach, these points are used in the when one variable is perturbed. Another approach is perturbation of all variables, so the points are set at the corners. But anyway, we treat the very unrealistic cases. And these are the drawbacks of this approach. But how we can assess the uncertainty, the sensitivity? The simplest way is just to draw the cloud of the points. For example, if there are two influencing parameters, two varied parameters, they are located within some cube. We plot the projections on the two planes, and there are such clouds. So it can be seen that the result does not depend on parameter Z1, but strongly depends on Z4, and less depends on Z2, Z3. Of course, that's a very unreliable way to treat the sensitivity. But even this approach is better in many cases than that's a perturbation approach. If we need some numerical assessment of the sensitivity, the simplest way are the correlations and regressions. The very popular approach is the Pearson correlation coefficient. The problem is it requires the output is linear. It depends linear dependence of the output on the varied parameters. First, that is not often the case, and actually there is, in my opinion, there is much better method is the regression. So when we try to fit our cloud of points by the hyperplane, by the least squares method, and this, in that case, the angle of that hyperplane to the axis will be our sensitivity coefficients. Once again, this works if the approach is close, if the response is close to the linear. If our response is not linear but quite monotonous, we can use Spearman's correlation coefficient. Actually, it's Pearson's correlation coefficient, but applied not to the values themselves, but to their ranks. That's where the requirement of the monotonicity goes. There are some examples when the Pearson correlation coefficient works and where it doesn't work. So actually, in such cases, not many sensitivity methods work. So, but if our response not monotonous even, what can we do? The most general approach is the perturbation methods. We drop the point somewhere and do not one perturbation, but a number of them, making paths within our cube of the input parameters. And wandering within that cube, we can assess the response of our model in different areas, and then find its mean value and the standard deviation. Generally, they will lie in some area. So here, for example, for some parameter, there is no influence. The standard deviation is quite small, as well as the mean value. So here, the mean value is not so big, but a high standard deviation. It means that the parameter itself does not influence much, but it seems to influence in combination with other parameters. And in this case, it's quite influential, high mean value, and relatively high standard deviation. So it's really influencing parameter. Well, the most widely used now are the variance-based methods. There are actually lots of libraries for example, for Python language that implement these methods. The idea is the combination of uncertainty and sensitivity analysis. We make the uncertainty assessment, and so the measure of the uncertainty is the variance of the output. And we assess the impact of each input variable or the group of variables into that overall variance. The first order indices is the impact of individual input parameters, and the total indices are for the groups of the parameters. In this case, there is a problem of how we do the sampling of our input data. Classical statistical models work with purely random sampling, but it seems to be not so good. There can be some more dense areas, more empty areas. Then the latent hypercube approach was suggested when we split our area into the hypercubes and do the sampling within cubes. The result is better, but still not perfect. There are still large blank areas and dense areas. So now generally, specially designed sequences are used to fill this hypercube, and the density increases evenly when we add more points to this hypercube. For example, the Sobel sequence, once again, a most popular approach now. There are once again Python libraries, but not all of them work, to be honest. I've tested some of them, so you should take care when you use them. Better test first. But here, the density is different, but every time our cube, hypercube, is filled quite evenly. But if you use this approach, traditional statistical methods won't work. They assume that our sample is classical. But the variance methods work well if we have sort of, well, a cloud, normal cloud. But if there is a clusterization or like quite complicated shape of our output, the results by these methods are unreliable. So that's why the graphical methods of the sensitivity assessment are important. So one should visually analyze the response to find which method should be used. So we need to go deeper and try to assess the probability density function of our output, depending on each varied parameter. Here, we compare the probability density function of output with variation of all parameters and with variations of all parameters but one. So it can be seen that this parameter is very influential, since if we remove it from the variation, the probability density function changes drastically. So there are different methods with their limitations. How do we choose the good one? So when we need to do the sensitivity analysis, first we think, what is the quality of interest? So we fix it, so we always remember, what do we study? Then, what are the input parameters? Are all of them independent? Since if there are not independent, we will need special methods for the sampling. What are the ranges and probability densities of our input parameters? It should be fixed and used in the sampling. Maybe there is some additional information about the model, which can help us choose our sensitivity method. And the very practical question, how long does the model run take? For example, if the model is simple, we can do thousands of model runs, but it is very complicated. We can make 2, 3, 4, 5, maybe dozen, but not more. We just have no time to do extra model runs. So considering all these assumptions, what do we choose? If our model is linear or quasi-linear, we can use the simplest local models, which I showed you on the slide how not to do the sensitivity analysis. Actually, that is the only case when they do work. And still, they should be used only if we have problems with time, with the possibility to run many code instances. Otherwise, even if our output is linear, we should stick to the regression-based models. If our response is not linear but monotonic, we can do, once again, regression and correlation models, but rank correlations, not for the values, but for their ranks. How do we find out this? Either we know beforehand by looking at the equations, or by running once, twice, or several times the set of the variations, and look at these clouds. If we do not know anything about our model, we have to do that perturbation method, building the paths within the cube. That's the best way. So, and nothing else to use. But if we know that our distribution is close to normal, there is a special tool, the Sobel sensitivity coefficients, which can be used. So once again, there are many libraries very widely used now, so you can just find a library, but once again, don't forget to test it. now we know how to choose the method for our sensitivity analysis. And we can do something useful with our multivariate simulations. There is a reverse. Sometimes there is a reverse problem when we do not want to find out the variability of the output, but we want to find inputs closest to the desired output. For example, when we do the tracer experiments, we need to identify the model, the sorption model parameters. So there are many factors, many equations in our model, many coefficients that can influence the output. So we can, so we need to find out the values of the model parameters that generally they reflect some properties of the medium that yield the experimental result or sufficiently close to the experimental result. This is done by the help of the optimization algorithms. I didn't remove this slide, although I've intended there are different proximity functions. So speaking of the proximity of the output to the desired one, there is quite large possibilities for the imagination. What is supposed to be close, especially if our result is not 1 point, but the temporal or spatial dependence or something like that. So the optimization started with the simplest methods. We just either wander within the input possibilities or just check them one by one. Long, tedious process. Then gradient-based methods emerged when we just try to go down, 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 down to the local minimum. The problem is that we go to the local minimum, not necessarily the global minimum. Then another group of methods emerged, the gradient-free methods. There we can do some jumps and hopefully reach the global minimum. And for now, the final result are the heuristic methods. When we, once again, we return to these wanderings, but more structured. So we analyze, they are generally based on some natural objects like birds' behavior, which try to get to the area with more food by looking at the behavior of other species or tuning of the instruments of the orchestra and so on. So we do some assumptions about the landscape and try to move along this landscape to find the minimum. There are many different methods. There is no time to explain them, and Valentina knows them better than me anyway. The problem with them, there is no perfect method. For different landscape, you should choose different method. And that's the problem, since here, the specialists in sensitivity and uncertainty analysis should work closely with the specialists doing the modeling of the physical processes. Since those who model processes know the landscape, and the specialists on sensitivity and uncertainty analysis know what to do with this or that kind of the landscape. So there is no such method that can fit all landscapes. Once again, sort of a checklist what to do before doing the calibration. Identify the variety parameters, their ranges, their distributions, fix the output, understand what is it. Is it a number, a matrix, a field, or tensor, whatever. What proximity function should be used for this output? Do we need to do the interpolation? For example, if we do simulation on sparse meshes, our results can be in different points than our experimental data. So we need to do some interpolation. For some numerical methods, it's done automatically, like finite elements, for some not. What is the sufficient accuracy for our task? Sometimes it can be derived from the experimental uncertainty, and sometimes, unfortunately, not. So we have once again used the expert judgment, looking at, yes, this is close enough, or no, we should look better. Now to some practical issues. The simplest issue is if you choose the uncertainty and sensitivity study tool, or if you want to design your own tool, you should keep in mind what code are you going to work with. Different codes use different input file formats. You will have to introduce your variables into the input deck of the code. So in the simplest cases, it's just a text file, no problem. In the more complicated cases, it can be binary file, a set of files, and sometimes it can be data like fields for initial conditions. So there are many different possibilities. So we should consider just a practical possibility to use a particular tool with a particular code. Another practical issue is the fact that I've already mentioned it. The value of interest can be represented very, very different. It can just be different. The simplest case, one value, no problem. But it can be the time scale. It can be some two-dimensional or even three-dimensional field. So even if you only want to prepare pictures for the report or for the article, you should consider that to choose the good visualization tool and so on. And I have already said that about the varied parameters. How well do we know their uncertainties? Ranges, distribution functions, the scale of the variation, and so on, and their dependence. And sometimes additional steps should be done, like choice of the sampling function for the dependent variables, and so on. Or maybe for complex distribution functions, so for these input parameters. As for the method choice, I think I have already said that, and I would like to stress that, for example, for the sensitivity analysis, there is a guideline. I have showed it to you. And for example, in the tool that Valentina created, for the sensitivity analysis, for each method, there is an explanation what this method does and what is it good for. For the optimization methods, no prescriptions. You should consult the doctor. In this case, consult the specialist on sensitivity and uncertainty. And once again, to the computation costs. Sometimes you can run code as many times as we want. So generally, we need several hundred at least code runs, but several thousand code runs to have enough population for the statistical assessment of the outputs. But in some cases, we just cannot do it physically. So then we make some points and try to guess what the response surface will be. And then if we find places where it behaves not as predicted, we can do code runs there, so locate our areas of interest. This approach was used in uncertainty management for reactor safety assessment by the French scientists. It was developed in the 1980s, I think, or at the very beginning of the 1990s. So that's my final remark. So that the best uncertainty and sensitivity tool will look like this. So in practice, we generally use just some subset of our options. So as for the conclusion, I think the main idea is that the specialists in modeling and in uncertainty and sensitivity should work closely together, but the specialists in modeling should know the very basics, at least the very basics of uncertainty and sensitivity assessment to be able to identify the uncertainties and to some extent to quantify them, especially for the input parameters. I think that's all. Thank you for your attention. I hope there's some papers that's on this topic and the contact details for Valentina. Thank you.
I understand that if you know much about statistics, you are not talking about artificial intelligence. But these black boxes we saw in these diagrams are a code that has inside, let's say, neural networks or decision trees, and we are not know what is going on in there. Or it's some methods that you already told us about, the analytical methods and mathematical models.
Well, there's the black box. From the point of view of the sensitivity and uncertainty assessment tool, the codes are generally treated as black box. But inside they're deterministic. But when we choose the methods, the knowledge of what's going on in the black box can be of great help, that linearity of the response or something else. As for the artificial intelligence, actually, speaking of that approximation here, the artificial intelligence can be of great help. I'm not sure if this approach is used in substantiation of in safety cases for the red waste disposal, but in the reactor safety assessment, now there is quite good development. Some methods were presented at the IAEA events. And my colleagues also develop such methods. And they seem to work, especially in identification of these areas of interest where so we put some dots, and then we, by the means of the artificial intelligence, identify the most interesting areas to do the code runs there.
Any more questions? I have one question. So here you said that you must make few hundreds or even thousands runs of the models, but how many parameters at once you can investigate? Is there any limit on the number of parameters?
In practice, we vary not more than several dozen models, the input parameters. The limit is that very dimensionality problem, that the more input parameters we vary, the bigger the uncertainty of the output. So I think there are some theoretical results on how the number of input parameters influence on the number of required code runs, but it's not the main problem. The main problem is the more we add the right parameters, the more the uncertainty range. So we should stop at some point, or our results will be just useless. We will go to the area when everything fails, but the probability of this event will be very, very low. So no practical use. So we should stop within the area of the probable enough input values.
Thank you. Any more questions? If not, then let's thank speaker again.
Thank you.
Thank you very much. And now we have a lunch break till 2 p.m.
Где он включается? Маленькая.